afternoon and welcome to a special live stream event covering the 2024 Quantum Future Awards, live from the Federal Ministry of Education and Research here in Berlin. So very good of you to join us online, and of course, good afternoon and welcome everyone who is here with us in the Alexander von Humboldt room at the Ministry. My name is Monica Jones. I'm a freelance journalist and TV news anchor, and it's my great pleasure to guide you through the proceedings this afternoon. As you know, quantum technology, very, very important for our future, for our economy, for society. And you probably also know that Germany would like to play a leading role in quantum technology in the world. And for that, we need bright minds, highly skilled professionals to lead us the way. And that is why in spring 2018, the Federal Ministry of Education and Research launched the so-called Quantum Future Program together with the quantum technology community in order to highlight progress, in order to make quantum technology visible to society, and also to highlight career opportunities in science, but also in industry. And the Quantum Future Awards are part of that program. And with it, the ministry wants to highlight and honor outstanding, innovative works by young scientists who are sitting here in the room with us. Now, the award honors master's and PhD theses that have a clear, and that is very important, application reference to quantum technologies. And the interesting thing about the Quantum Future Awards is that we don't know the winners yet. That's going to happen now in the next 90 minutes when those young, bright scientists will present their works here in front of us in very short pitches of 3 minutes each. And I've mentioned you so often, so hello, you're feeling okay? You're feeling good? Looking forward to it? So there's a lot of smiles here. You can't see them yet, but you will see them on stage. And the winners and the runners-up in both categories, they will, of course, receive awards. For one, we have those beautiful glass cubes here waiting for them. That's for the winners in both categories. And the runners-up will also receive something, namely a study trip worth of 4,000 euros. The winners get a study trip worth 6,000 euros. And since 2021, and that is very important for everyone in the live stream, the ministry has also launched the popular vote or the audience prize. And that means that you can play a decisive role in picking the finalist who will receive the popular vote and also receive a prize, of course, a further training opportunity in the field of science communication. So please do pay attention. Please keep a notepad ready in order to take down which of the pitches you think is the absolute best. And there should also be a list in the live stream that has the names of everyone who is on stage here. So do take notes so you remember who you liked best. And of course, we have a jury of experts here with us, and they're already here on stage. Let's meet them. I start with ladies first, namely Dr. Heike Riel. She is an IBM Fellow, Head of Science of Quantum and Information Technology, and Lead of IBM Research, Quantum Europe at IBM Research. Then to her right is Dr. Thomas Strom, who is Senior Research Scientist and Chief Expert for Quantum Technologies at Robert Bosch. So the two of you, you are the industry representatives of the jury. And then we also have a representative from the world of science, namely Professor Dr. Jens Eisert. He is Professor of Quantum Physics at Free University Berlin, affiliated with Helmholtz Center Berlin, Heinrich Hertz Institute. And previously, he also was a professor at Potsdam and a lecturer at the Imperial College in London. And thank you very much for taking the time. And I just have to ask this. I've mentioned already that application is important. What is the main criteria when you hear those 10 pitches later on? What's the main criteria that you will be looking for?
So we have been reading through all these theses, and they're really excellent. And the main criteria, there are a couple of which we are looking at. Of course, a very, very important one is the technical and the scientific output and outcome. Then also the form of the thesis. And today we will be very excited to hear then the presentations. And as you mentioned before, the application. Because the Quantum Future Award of the BMWF, it's really also about the application. Can you apply it also in the industry and the relevance and importance of this?
Of course, I think we should stress that everybody who is in the room, all the finalists, in their own way, are already winners because they're amongst the top 10. But surely you have a favorite already, do you? Does anyone have a favorite?
No, I don't. Maybe unsurprisingly, they're all very strong.
Okay, so you're open.
I'm open.
Yes, I think we are very well informed, and we also had discussions, but the race is completely open. We have no decision so far.
Okay.
So it's very important to perform also in the presentation.
No pressure.
No pressure. No. You stay relaxed. You're all fantastic. So, yeah, thank you so very much for your time. And of course, there is a fourth jury member. There are more in total. But the fourth jury member represents the world of politics, and she is also our host. So let's give her a warm welcome, namely the General Manager for Technological Sovereignty and Innovation at the German Federal Ministry of Education and Research. Hello, Dr. Tina Klüver.
Hello, everyone. Good afternoon here in the room, but also to those of you joining us virtually. Very happy to be here today for this fine ceremonial occasion. Dear members of the jury, and most importantly, the honored finalists, it's my pleasure and to welcome you all here to the grand conclusion and presentation ceremony of the Quantum Future Award 2024. I'm delighted to welcome the jury, our finalists and the guests here at the BMBF in Berlin today. All of you, our honored finalists, have decided to carry out research in the field of applied quantum technology. And that's for very good reason. We are well aware of how incredibly important this topic is for our future. We know that quantum technologies will change our lives, will change the way we communicate, we eat, and we live. In the future, quantum computers will be able to solve specialized, highly complex problems. Quantum sensors will allow us to take extremely precise measurements. And quantum communication will make data transfer more secure and reliable. Just a few days ago, I was lucky enough to witness the activation of a new quantum communication channel between Berlin and Bonn. What we also know is that a lot of work is still required before such applications become reality. It is time to tackle the remaining scientific and technological challenges. That's why we need you, young scientists like you, who use their knowledge, talent, and passion to develop quantum technologies that can be put into practice, who help advance our society, who think outside the box. That's why we at the BMBF have been using our Quantum Future program for a number of years now to fund the next generation of researchers in this field. The Quantum Future Academy offers students fantastic opportunities to establish networks with relevant companies, while the Quantum Future Junior research groups give young academics the chance to lead their own independent scientific research group. We have also implemented further specific measures to meet the problem of the skill shortage in the field of quantum technology. In the future, we will expand these activities in a coherent approach under the heading of Quantum Future Professionals, in order to, firstly, identify the quantitative and qualitative demands of the quantum technology sector. Secondly, create educational opportunities that span the entire range of a person's career, from low threshold activities that inspire school pupils already to take an interest in this technology, to the development of advanced training opportunities for interdisciplinary system engineers. Thirdly, make the range of programs currently on offer within the complex German quantum technology ecosystem transparent and accessible to interested skilled professionals and companies. We are well aware it's not always that easy. And fourthly, activate existing talent pools and highlight Germany's attractiveness and strength to improve the recruitment of qualified personnel. And I've not yet mentioned, you will definitely notice, the element of our program for supporting the next generation of researchers in Germany, the Quantum Future Award. It is the reason that we are all here today, on screen and on site. This is already the 7th time that we will present the award. All of our finalists submitted their master's to doctorate thesis and have convinced our expert jury. Their projects stood out from all the many others' applications with their excellent scientific quality, composition, and practical relevance. So I can definitely say you're all winners already. Congratulations to making it to the finale. All of us here in Berlin and those joining virtually can't wait to watch your presentations. You each have just 3 minutes time and one single slide for your presentations. We know that this is a big challenge, but we are sure that you will solve it masterfully. When I say we, I speak not only for the entire BMBF, but also for the jury, which I'm honored to be a part of today. I would like to take this opportunity to thank the members of the expert panel. Heike Riel, physicist and head of Science of Quantum and Information Technology and lead of IBM Research Quantum Europe at IBM Research. Jens Eisert, a physicist specializing in quantum information theory, ERC fellow and professor at Freie Universität Berlin. And Thomas Strom, physicist and chief expert for quantum technologies at Bosch Research. Over the last few weeks, you have read our finalist theses in detail and used your expertise to conduct a thorough evaluation. You are here today to listen to the finalist pitches together with me and then to decide on the winners of this year's Quantum Future Award. I'm sure it's going to be a tough challenge for us. Given the outstanding quality and the competition interest, it will certainly not be an easy task. So I'm delighted to have such renowned experts by my side. But I don't want to keep you waiting any longer. I wish everyone here in Berlin and all of our viewers at home an exciting, entertaining, and enlightening afternoon. And the best of luck and success to all you finalists. I hope you have fun giving your pitches. Thank you all so much for your hard work and commitment. Let's get started.
Thank you. Thank you very much, Dr. Klüver, also for giving them a lot of courage. We've tried it before. You're all fantastic. You will all enjoy your time here. We are ready for our first round of finalists, and we're starting with the Masters category. In both categories, we have 5 finalists. They all have 3 minutes to present their pitches to the jury members and to the audience. We also have a few guests here in the room, so they're also presented to you, of course. And for the audience, online as well as the guests here in the room, again, the reminder, make sure that you have a notepad or maybe your mobile phone, if you take notes in there, ready, so you can note down which of the pitches you think is the best and worthy of the popular vote. Ready? Okay, then let's start the first round. And our first finalist is Jacopo de Santis. He completed his master's degree at Technical University Munich. The title of his thesis, Design and Characterization of a High-Finesse Optical Resonator for Cavity-Assisted Readout of Atomic Arrays. And I'm told that this is highly, you may come, don't you worry, that it's highly relevant for the field of quantum computing. So, Jacopo, find your space and your 3 minutes start now.
Well, utility-scale quantum computation requires quantum error correction. And for this particular application, neutral atom arrays are a very promising platform, thanks to their high scalability, long coherence times, and all-to-all connectivity. However, a problem for cyclic error correction, where the errors are detected and corrected in real time, is atomic qubit states readout, which needs to be both improved and sped up. At the Max Planck Institute of Quantum Optics, we plan to do so with an optical resonator, whose design and realization has been the main focus of my master thesis work. But what is an optical resonator? Well, in its simplest form, it is an optical resonator, or an optical cavity, is made up by 2 mirrors facing each other, just like the infinity mirrors you sometimes find in the bathroom of hotels. And when you are in one of those rooms, you see yourself reflected onto those mirrors an infinite amount of time. This happens because the light gets trapped into the resonator and the photons are bouncing back and forth between the 2 mirrors continuously. This is exactly the fact we want to take advantage of in order to enhance atom-photon interaction. And this happens provided that the volume in which the photons are confined inside our resonator is small enough. And by taking this geometrical consideration into account and other consideration regarding mirror reflectivity, system stability, electric field shielding, and interference phenomena happening on the electric field inside of the resonator, I came up with the design that you can see in the model. And in the picture below it, you can see its physical realization after I built it and integrated it into our experimental setup. Please note this small red dot in the middle is our magneto-optical trap, a cloud of over 1 million atoms, of rubidium atoms trapped together, from which we will extract our qubit array from quantum computation. And to conclude, I'd like to highlight the advantages that an optical resonator could offer for qubit state readout. Traditionally, when you want to read out the state of one of your atoms in the array, you shine near-resonant light onto it and detect this fluorescence through an objective. However, how it is already clear from the schematics, only a small fraction of this photon is actually detected. On the other hand, if we place the atom inside of an optical resonator, what we will do is that we will effectively change its emission pattern, thanks to a phenomenon that's called the Purcell effect. And thanks to this, the atom will preferentially emit inside of the resonator mode, allowing us to detect a much higher fraction of the photons. And this has a clear advantage both in locality and in speed of our qubit state measurement. The application of this better type of measurement is both for mid-circuit measurements in quantum error correction code or optical intercorrection of quantum processing units in distributed quantum computing. Thank you.
Thank you, Jacopo. Thank you so much. So that was the first entry, Jacopo De Santis. Our next finalist is Julia Dräger. She completed her master's degree at a technical university in Munich, and the title of her thesis is NMR Microscopy using quantum sensors in diamond. And here it says that her thesis may yield different applications for NMR microscopy of biological samples or material sciences. And you'll explain it all to us, Julia. Once you have found your spot, then I can say your 3 minutes start now.
Good afternoon. Thank you for the kind introduction. When it comes to diagnosing and understanding cancer, two powerful techniques stand out. In hospitals, magnetic resonance imaging, MRI, or in German, MRT, is a standard method for visualizing soft tissues, making it a key tool in diagnosing cancer. In research, optical microscopy is invaluable for its high-resolution images, allowing scientists to observe cancer cells in great detail. However, it does miss out on MRI's comprehensive information. Currently, there is no way to combine these two methods, which means that we lack a complete picture of cancer down to the cellular level. Yet, understanding how each individual cancer cell behaves is crucial for revealing the underlying processes that drive the cancer and to enable early-stage cancer diagnostics. In my master thesis, I built the first of its kind MRI microscope, capable of detecting MRI signals spatially resolved on the length scale of single cells. This breakthrough was only possible by using the unique properties of quantum sensors. In our case, we use atomic-sized defects in diamond that you can think of as tiny compass needles. And to achieve both high resolution and high sensitivity, we combine more than 100 trillion of these sensors, which is far more than we have stars in our galaxy, as a network across the diamond surface. From there, these sensors detect incredibly weak magnetic fields from the sample and encode them into a photoluminescence movie, which we capture with a high-speed camera. Combining the detailed insights of MRI with the speed and resolution of optical microscopy is a step towards a new generation of imaging. It bridges the gap between medical diagnostics and research, one cell at a time. The prize money will allow me to continue this journey further by applying our technique in collaborations with experts in the field. And in particular, I want to join the group of Professor Rachel McHenry from UCL in the soon starting Quantum Biomedical Sensing Research Hub. Thank you for your attention.
Thank you, Julia. Thank you very much. So our second pitch there, Julia Dreger. And we come to our third finalist here in the master's category, Jana Fölisch. She completed her master's degree at Karlsruhe Institute of Technology, and the thesis is entitled State-of-the-Art Quantum Optimization, an application to the car sequencing problem. And it explores the potential of quantum computing, specifically the quantum approximate optimization algorithm for a complex scheduling issue in automotive production. And I'm sure you can put it in much better terms. Jana, you're ready to go. So your 3 minutes start now.
Thank you, Monica. So German cars, they are more than just vehicles. They are a symbol of pride, a symbol of excellence engineering, and also a cornerstone of our economy, supporting millions of jobs. However, our automotive industry today is at a crossroads because global competition and electrification are driving and demanding efficiency more than ever. Yet, inefficiencies in our production lines, they are costing us millions. One culprit here is the sequencing of cars. It's not just about finding an optimal order, it's about managing constraints. Each station and production cyclus has unique capabilities, and cars vary in models, features, configurations, each demanding tailored assembly steps. So optimizing this whole process means managing and synchronizing all these elements together to maximize OEE, the so-called overall equipment effectiveness. In my research, I modeled this so-called car sequencing problem with real-world constraints, and then I used real quantum hardware and QAOA, the quantum optimization algorithm, to run it and to calculate it. That was something that was never attempted before. The aim was to assess how far we are from using quantum optimization to address real-world industrial challenges, like this is one. The results were kind of both, sobering and promising at the same time. For a small instance, like sequencing 3 cars, QAOA delivered feasible solutions. QA delivered a feasible solution. However, when we scaled this problem, there were interesting challenges revealed. So one of this was, for example, the scalability gap, because for a real industrial scenario, we would maybe consider around 200 cars. In scaling this up, we would need more than 40,000 qubits, an amount that is not available right now, at least right now. And also, there are other problems and challenges. For example, the quantum computer has to address and manage and tackle with information loss, with qubit coherence, or also with the complexity of the circuit. But as our algorithms are getting better and better in dealing with all that noise, and we can regularly see new ways of how to map optimization problems to quantum computers, the results are overall improving, and this improvement is pretty important for the automotive sector, because even a 1% improvement in OEE can result and could translate into hundreds of millions for revenue. So securing jobs and also protecting and securing the financial stability. And I think with that, I'm at the end.
Thank you. Thank you, Jana. Jana Fölisch there, and it just shows you 3-minute pitches. That's real art, and you don't have cue cards like I do, so well done to all of you up until now. Our fourth finalist is Maximilian Johannes Kramer. He completed his master's degree at Freie University in Berlin, and his thesis is entitled On Quantum Algorithms for Satisfiability Problems. And in there, he proposes a hardware-friendly, self-correcting quantum algorithm for satisfiability problems. So we're very curious to hear that. Maximilian, you ready?
Yeah, I'm ready.
Then your 3 minutes start now.
Solving computational problems and optimization basically determine our everyday life. And over the past years, we've seen how the size of problems that can be solved on modern computers has significantly increased. However, it is believed that certain computational tasks are intrinsically hard to tackle on classical computers. This is where quantum computing comes in, a new paradigm that uses a fundamentally different set of operations. And as such, it has been proven theoretically that quantum computers offer an advantage for certain tasks. So people are building and realizing quantum computers, but they are still very limited in their capabilities. That means we cannot yet solve relevant problems that classical supercomputers cannot. So if our aim is to develop quantum algorithms that are useful as early as possible, I think it's fruitful to consider two ingredients. First, we should look at a problem which is relevant. And in our work, we focus on satisfiability problems which have many applications in industry, with examples being hardware and software verification, planning and scheduling, but also many more. But besides being relevant in industry, there's also a rich theoretical background on them. And as such, I think they are an ideal testbed for quantum computing and applications. Second, when designing quantum algorithms, we should look at the classical side. We should look at classical optimization and algorithms design. So what can we learn from the classical side? A, let us step back a second. We will not solve satisfiability problems efficiently on on quantum computers, as they are also very hard on them. But let us realize one important thing. Not every instance of a generally hard problem is actually hard to solve. So let us try to understand the structure that makes some instances easy with certain algorithms. B, when designing quantum algorithms, let us directly make them hardware friendly and let us adapt them to the hardware that we have. And we see exactly this trend in classical computing, where hardware efficiency was surely important in the beginning of the field, but it is still relevant today. See, for example, the current AI developments, which are only possible because specialized hardware, in this case GPUs, exist. So the importance of developing hardware-efficient methods for quantum computers as well cannot be overstated. And this is not just relevant for short-term breakthroughs, but also for the long-term progress of the field. And with our work, we contribute to exactly this. We contribute by proposing and analyzing a hardware-friendly, self-correcting, near-term quantum algorithm for a practical problem. But there is more. We also developed a deep theoretical understanding of why this algorithm works so well. And since we use the design principles from the left, I'm convinced that it has applications both on near-term devices and in the long run. And in this rigorously motivated spirit, let us make quantum computing practically useful.
Thank you. Maximilian Johannes Kramer. So, we have the fifth and final finalist in the master's category coming up now, and his name is Lukas Sturm. He completed his master's degree at Technical University Darmstadt. His thesis is entitled Neutral Atoms in Large Interleavable Dipole Trap Arrays, and the setup successfully demonstrated over 1,000 atomic qubits, setting a milestone in this quantum computing architecture. That sounds promising, Lukas. You're good to go?
Yeah.
All right, 3 minutes, start now.
So yeah, when I think back to my beginnings in quantum computing, the very first thing I remembered, or the very first thing I've learned, is David DiVincenzo formulated 5 general criteria that must be fulfilled for the experimental realization of a quantum computer. And actually the first criterion he's mentioning is scalability. And this is exactly where my work comes in. The milestone of 1,000 physical qubits has been considered an important goal for a long time, but if we take the distinction between logical and physical qubit into account, even higher qubit numbers will be required in the future. And this goal is a challenge for all of the approaches, and whether they are based on semiconductors, superconducting circuits, ions, photons, all of them are facing the same challenges. Our approach is based on the use of neutral atoms. Neutral atoms can be understood as intrinsic identical qubits and offer several advantages, but if we have a look on the scalability, it is the fact that neutral atoms can be trapped using tightly focused laser beams. And these can be generated by a simple lens. So this also means that when we have a look at such a lens here, that each lens translates to one trap site and therefore potentially to one atomic qubit. And this whole system can be minimized and scaled up wonderfully by just placing multiple lenses next to each other. In our case, we call them microlens arrays. These systems are often limited by the available laser power. So therefore, the idea was to overcome this limitation by using multiple independent laser sources, but at the same time. And in this context, we were able to show that it is possible to generate these trap arrays independent from each other and then superimpose them afterwards. The result is a much denser and larger trap structure, which is highly scalable with the number of available laser sources. And if we use these trap arrays in combination with additional optical tweezers, we can do some rearrangements. And for example, we can rearrange such clusters here of 3x3 atoms, and these could be useful for the error correction applications, for example. And in this particular case, we were able to provide up to 1,305 atoms, and in the case of this 3x3 cluster arrangement, even up to 441 atoms can be realized. But in order to come to an end, I was part of the race for the highest qubit numbers. We were the first ones to exceed the 1,000 atomic qubits barrier, and I'm looking forward to surpass other upcoming milestones in the future. Thank you.
Thank you. Thank you, Lukas. Lukas Sturm, the fifth and final finalist in the Masters category. And I hope everyone online and also our guests here, you already made your notes so that you can remember who did what and what impressed you the most. All right, let's take a deep breath because we now move on to the next category, which is the PhD or doctor's thesis category. And again, we have 5 finalists. And again, they have 3 minutes to present their thesis and their work. And we start with Dr. Andres Gritsch. He completed his doctorate at Technical University in Munich. In his thesis entitled Erbium Dopants in Nanophotonic Silicon Waveguides and Cavities, he established a novel material platform for quantum technologies, which is highly promising for a hybrid approach to quantum information processing. And the rest I leave completely to you. You good to go?
Yes. Thank you very much.
3 minutes start.
Silicon nanophotonics has the potential to become the most scalable technology for quantum information processing out there. Let me explain you why. So the first factor here is silicon itself. As we all know, the digital revolution, or the first quantum revolution, was enabled by nanostructured devices made from silicon. Because of that, today's manufacturing capabilities of such devices are simply unrivaled by any other material platform. In addition, highly purified or even isotopically purified silicon has excellent promise for quantum memories with good coherence. The second important part here is the optical addressing of different quantum memories. Because of the short wavelength of the optical fields, this allows dense integration with no or negligible crosstalk. In addition, this paves the way for photonic quantum gates, and because of the versatile photon routing opportunities, which can be even done at room temperature, this allows for modular quantum architectures. These architectures are known for their extremely high connectivity, which is a scaling advantage because it reduces the threshold for quantum error correction. So the question here is, why are we not hearing a lot more about silicon nanophotonics in the context of today's quantum technologies? And the reason for that is that until a few years ago, there was just no emitter known or no optically active spin known that would allow us to control quantum memory states, long-lived quantum memory states with optical fields. In my PhD project, I could cut through this by demonstrating that erbium dopants can be integrated in nanophotonic silicon devices. By doing so, I could prove the existing or the established scientific opinion wrong that this is not possible reliably, and the sites that I found, they even showed promising properties for quantum technologies. I could then go even one step further and build a prototype of a scalable, efficient spin-photon interface, which you can see here. So this comprises a single spin qubit, which is the erbium dopant, embedded in a nanophotonic resonator fabricated on a single silicon chip. Now, using such a device, I could show optical spin initialization. I could demonstrate the first ever optical signature readout of a spin qubit in silicon. Furthermore, I could demonstrate that coherent spin rotation, so one-qubit gates, are possible on this material platform. And then I could demonstrate that the excitation process to the optical state itself is also coherent. This now sets the stage to extend this to a larger testbed of multiple of such devices. The silicon photonics, nanophotonics background here allows us, of course, to do this much more rapidly and with a much higher number of such interfaces. On top of that, the telecom transition here allows us to work with photons that are compatible with optical glass fiber technology. Thank you very much.
Thank you. Thank you, Andres. So, Dr. Andres Gritsch, our first finalist in the PhD category. The second finalist here is already ready to jump to the stage, Dr. Sascha Heusen. He completed his doctorate at RWTH Aachen. His thesis is entitled Applications of Fault-Tolerant Topological Quantum Error Correction in Near-Term Devices. And, so it says here, his work pioneers the transition of fault-tolerant quantum computation from theory to application and from university labs to commercial value. How? Why? This is what we find out now. Your 3 minutes start now.
There is no advantage in using quantum computers over classical computers, unless you get rid of noise. Qubits are fragile and prone to errors. They must be well isolated from their environment in order to maintain their state. But at the same time, we need some access to them in order to perform computations with the qubits. This balance is what causes noise or errors. And noise really is a terrible opponent. Try telling a joke to your friend in the middle of a heavy metal concert. If you don't have a microphone in a room full of people, you don't get your message across. If you run a beautiful, sophisticated quantum algorithm, you might still end up measuring just random bits that contain no information. You lose your result if your computation is drowning in noise. The best theoretical estimations of how good a qubit can become is about 1 error in 1 million operations. To run useful quantum algorithms, we believe that an error rate of at most 1 error in 1 trillion operations is required. This mismatch is equivalent to the size of the Eiffel Tower versus the width of a human hair. Quantum error correction is the framework that allows us to bridge this gap, to suppress noise in a systematic and controlled way. The way to build large-scale fault-tolerant quantum computers with practical commercial use. I have conducted 4 projects that help making fault tolerance and quantum error correction reality. During my PhD, we have shown in collaboration with experimentalists the world's first realization of a logical qubit that is noise protected with fault-tolerant universal control in an ion trap quantum processor. This means that it can run any quantum algorithm efficiently without introducing more noise. In a follow-up work, we provide concrete guidance for the architecture design of next-generation experiments with even stronger noise suppression. For the first time, I have developed practical quantum circuits for error correction that are well suited for the small quantum computers with less than 50 qubits that already exist today. We avoid slow mid-circuit measurements completely that would otherwise interrupt the algorithm. Yet, we respect the fault tolerance design rules, which was previously thought impossible in the community. Lastly, I have developed a noise simulation technique that is efficient in this regime of extremely low error rates. These simulations currently run for days or even weeks on large supercomputers, but with our method, you can run them within minutes on your own laptop. This reduces time and energy footprint substantially. The impact is clear. My work bridges theory and real-world use cases for science and industry. It advances quantum computers to reliable, large-scale systems, bringing us closer to the practical application of useful quantum algorithms. Thank you.
Thank you, Dr. Sascha Heusen. So that was our second finalist in the PhD category, which means we now move on to the third finalist in the PhD category, and that is Dr. Christian Hölzer. He completed his doctorate at Ludwig-Maximilians University in Munich. The title of his thesis, Realization of Alkaline Earth Circular Rydberg Qubits in Optical Tweezer Arrays, and it is highly relevant for the field of quantum computing. So, Christian,
yes, thank you.
3 minutes, start now.
All right. To begin with, I actually did my work at the University of Stuttgart. So, but it is really an honor to be here today and present my work I did during my PhD. So my project was to build a quantum simulator experiment based on the neutral atom platform. And we already heard a bit about the neutral atom platform here, but really the thing is that you encode qubits in single atoms which are held in position by at fixed position and controllable position by highly focused laser beams. And this flexibility have given them most of the prominent spots in building a quantum computer and or quantum simulators. And now to let these qubits talk to each other, so-called Rydberg states are used, which are really like macroscopic objects, like where the orbital or the electron orbital is blown up to the micrometer scale. And in state-of-the-art devices, typically like s-orbital Rydberg states are used, as you can see up there. But the problem with these is that they decay on the microsecond scale, which fundamentally will limit the coherence time we can achieve in such systems. So we overcome this problem now with a trick, and we spin up the electron and shape its orbital into a ring. And this increases their lifetimes by about a factor of 1,000, and these so-called circular Rydberg states now can live in the millisecond regime. But to fully harvest now these properties, we also need them to shield them against thermal radiation, which is all around us. And therefore, I built and patented a quantum processor unit, specialized design here, which incorporates, among many other things, transparent microwave cavity where you can look through and also shoot all your lasers through. And in the center, now where we trap the atoms between this cavity design, the thermal radiation is switched off. And this now allowed us to measure the longest living Rydberg states ever recorded in a lab with about 5 milliseconds of lifetime, which you can see is orders of magnitude longer than what we would expect from an s-orbital Rydberg state. And there is another feature, another great advantage of using circular Rydberg states if you combine them with using them with alkaline earth atoms with 2 valence electron systems. And because this circular orbit is so far detached from the second electron orbit, the second electron just looks like an ion. So this means we can now transfer all the successful methods and concepts from quantum computing with ions to our highly flexible system. So we think all in all, our work is really a crucial step to build the next but one generation of quantum computers and quantum simulators on the neutral atom platform. Thank you very much.
Thank you. Just one question. So you started the work at the University of Stuttgart, but you completed it at the Ludwig-Maximilian University in Munich. No.
Still at the University of Stuttgart.
You're still in Stuttgart. So I just needed to clarify that. Okay, we don't want to take that away from the University of Stuttgart. Thank you so much. So now we move on to Dr. Patrick Huber, who hopefully completed his doctorate at the University Siegen. The thesis is entitled Multi-Qubits Gates in a Trapped Ion Quantum Computer. It's highly relevant for the field of quantum computing and quantum machine learning. Yup. You're good to go?
Yes.
Then 3 minutes, start now.
And also thank you for the previous speakers, because by now we know the importance of quantum computing to begin with. So let's hop on to our system. So our system is a trapped ion-based quantum computer using RF control of the qubit systems. A crucial feature of a trapped ion quantum computer in general is the inherent all-to-all connectivity between all qubits in a register. Over here, I worked with a register of 4 qubits, and actually the name is stolen from the classical computer science. So we do have 4 qubits in a register, which we now need to control to implement quantum circuits. We already have seen some of those today. Okay, the crucial point is that in such systems, we do have the all-to-all connectivity basically always on in this case. And now comes the problem, we need to tailor this always on connectivity to the demand of the quantum circuit that we actually want to run. For example, there might be occasions in quantum circuits where we would like to execute a conditional dynamics in, let's say, in parallel. Therefore, I used a technique, or extended a technique to protect the quantum information, namely the dynamical decoupling technique, such that we can on the fly reconfigure our quantum register to go from a configuration which is like a power core configuration with auto-OR connectivity to, let's say, a sub-register configuration which can be seen as a multi-core CPU if you wish, to efficiently implement quantum circuits. So this we could demonstrate also on a system of 3 qubits where we do actually not execute a quantum circuit which is quite lengthy as we have seen it here, but instead use this auto-OR connectivity to directly implement 3 qubit dynamics to reduce the length of the quantum circuit to execute, while also reducing the execution time. And we have here till now that the timing, so lifetime of quantum information is a limiting factor, and therefore reducing the circuit's runtime also contributes to its success probability in the end, which we have also heard is a crucial parameter to optimize in future quantum computers. So I hope my work could actually help to improve quantum computers in future and bring them more close to reality. And with that, I'd like to conclude, and thanks for your attention.
Thank you. Thank you, Dr. Patrick Huber. You were number 4, which means we have one more finalist in the PhD category, and that is Dr. Andrej Kurdzic, who completed his doctorate at Friedrich Schiller University in Jena. His thesis is entitled Quantum Key Distribution with Entangled Photons in Daylight. It is the first feasibility study of the entanglement-based QKD in daylight from an orbiting satellite, and therefore it is highly relevant for the field of quantum communication. I'm not saying your second name again, I'm just saying, Andrej, you have 3 minutes. The 3 minutes start now.
Thank you. So quite ironically, I will actually talk about how to defend against quantum computers. So nowadays we live in the so-called information age, where data security is more important than ever. Governments, healthcare, banking, defense, all these sectors rely very critically on secure communication and data transfer. However, quantum computer poses a threat to traditional cryptography. On the other hand, quantum key distribution, or QKD, offers a solution. In QKD, security of cryptographic keys is based on the laws of quantum mechanics. Quantum states cannot be copied without introducing errors into the system. And this feature allows communicating parties to detect potential eavesdropping, making it secure. Entangled photons are particularly suitable for generating cryptographic keys because they behave in a correlated manner even when separated very far apart. Now, optical fibers could be used for transmission, but they are not always available. Furthermore, absorption in optical fibers limits practical QKD to distances of a few hundred kilometers. An alternative is free space transmission, for example, between buildings in a metropolitan area or between a satellite and ground. A major challenge of free space transmission is atmospheric turbulence, which causes random and very rapid movements of your photon beam at the receiver. But an even bigger challenge is how to distinguish these extremely weak quantum states of light in the presence of much, much stronger daylight. Therefore, most experiments up to date have been limited to nighttime operation only. During my thesis, I contributed to a development of a complete QKD system for free space applications on ground. And my particular contribution was the QKD receiver, which included beam stabilization and spatial filtering functionalities, which finally enabled optimal daylight performance. The performance of the complete system was demonstrated over a test range, free space test range of 1.7 kilometers, where 2.5 kilobits per second of a secure key rate was achieved in direct sunlight. Now, this is an order of magnitude improvement of both the link distance and the secure key rate for a quantum entanglement-based system. In addition, I developed a tool for simulating QKD from an orbiting satellite. And using this tool, I showed that satellite-based QKD in daylight is actually within reach. However, further technology developments are necessary. Now, I would like to conclude by noting that the methods developed in my thesis can be extended beyond applications in QKD on the goal towards ultimate quantum internet, which will connect many quantum computers all around the world. Can you imagine internet that only works at night? Thank you very much.
Thank you. Dr. Andrej Krjic, thank you so very much. And that was our 5th finalist in the PhD category. We had 5 fantastic pitches in the master's category, 5 fantastic pitches in the PhD category. I watched the jury members, and they did exactly as I told them to do before the event started, namely they all kept their friendly poker face. I have no indication which of the pitches sort of convinced them the most, but this is a task that they will have to tackle now in the next 10 minutes. We will take a break here because the jury members will go into a room all on their own, compare notes, discuss, heated discussions perhaps, and then in 10 minutes' time, we will find out who the winners and the runners-ups are in those 2 categories. And for everyone online and also the few guests that we have here in the room, you too have 10 minutes to decide who you think is the best, not per category, but simply the best, in your opinion. And don't forget to submit your vote, because after 10 minutes, the lines will be closed, and then you can't vote anymore. Okay, I keep my fingers crossed for absolutely everybody who did fantastic pitches up here. And yeah, we'll see each other again in 10 minutes' time. Welcome back. Those 10 minutes were slightly longish 10 minutes, which is interesting, but the jury members just re-entered the room. Now, whether the fact that the 10 minutes were a bit longer than you would normally consider 10 minutes to be, is a sign for heated discussion, or whether there was so much agreement that they just had to go through it again to make sure. I don't know, but this is something I would definitely like to know. I can tell you, though, that we have a popular vote already because the lines are closed and we're just checking it, but that we keep for the very end. So, one winner is already established. And the others, namely the two runners-up in the PhD and the master's category, as well as the winners in the PhD and the master's category, will be revealed very, very shortly. And for that, I need assistance. And I would like to call back to the stage Dr. Heike Riel, Dr. Thomas Strom, Professor Jens Eisert, and Dr. Klüver, our jury members. Please, do join me on stage. And I can see at least one jury member, 2, 3 have headsets. And Dr. Klüver, we have a microphone for you. And we also have a second microphone, as I mentioned to you earlier, to our finalists. Of course, when you pick up an award and you would like to thank somebody or say something, then we do have a microphone here for you. But I would like to keep the suspense just a little bit longer. I would like to know from you, what's the reason? Why did you make us wait that long? Was it so difficult to come to a conclusion?
Because we only have winners.
So they were all too good.
It was really, I mean, excellent presentations, excellent work, scientific outcome in the thesis and everything, right? And very, very tight field.
Okay, but you did find 2 winners and 2 runners-up.
I mean, we're still alive, but we fight it.
Okay. I'll be very curious to find out. Perhaps, but let's just put it to the test. So let's start with the master's category and with the runners-up in the master's category. And I think, Dr. Strom, you have the paper for the runners-up in your hands already, and you can reveal his or her name to us.
Yes. I'm happy to announce the winner in the category Master Thesis, second place. And this is for Julia Dräger.
Congratulations, Julia Dräger. So you remember that it's a course, an excursion worth 4,000 euros that you win, and also obviously this beautiful certificate. As I said, if you would like to say something, you have the chance now.
Yes, I would. First, thank you so much for awarding me the award. I'm very, very thankful. I'm also super thankful for my parents to always encourage my interest in natural science, and of course my supervisor in the master thesis, and now luckily also my supervisor in my PhD project, Professor Dominik Bucher, and all of my colleagues back home who maybe have watched or are still in the live stream. It is a pleasure working with you every day, and thank you so much.
Fantastic. Congratulations. Please to stay here with us. We have a runners-up in the PhD category as well, and I think, Professor Eisert, you're the one who knows his or her name.
Yes,
well,
I
actually
do.
only his name, because we only had gentlemen.
As I said, it was like an extremely tight race because all 5 presentations were extremely convincing, and also the material was extremely convincing. In the end, we had to make a choice, and we kind of awarded the second place award for a very impressive, well-motivated work that is extremely practically relevant, and the name is Christian Hölzel.
Christian Hölzel from Stuttgart University. Congratulations.
Congrats.
And of course the same, would you like to thank Stuttgart University or anyone else? Then we would, of course, give you a microphone to do so.
Yes, it's a great honor to receive this award here, and I want to thank the people back home, so my team and my supervisor. Without them, this would not have been possible, and also Jenny, who is here and then has come to here with me to Berlin. Oh, thank you all.
To give you support. Well, yes. Thank you so much for that. And now we come to the winners. Let's start in the Masters category again. The winner in the Master category, Dr. Riel. Who?
It's my really great pleasure, and as has been said, it was a tied race, and it's my pleasure to now announce the first winner of the Best Master Thesis. And the winner is of the Quantum Future Award 2024 in the category of Master Thesis is Maximilian Johannes Kramer. Congratulations.
Congratulations.
Congratulations, you have done a great job in bringing theory to making it work for applications and, make quantum computing work. Congratulations.
And of course, with the winners, we also have one of the glass cubes. Just make sure you pick the right one.
Oh, that's... Okay, how do I see it here?
This one.
Oh, it's not connected. Ah, okay, now I got it. So, yes, it's my great pleasure to carry you to... Congratulations. Very well done.
And now, Maximilian, of course, you have both your hands full. If you would like to say something, then I will just assist you. Here
Perfect.
we are.
Thank you. Thanks also to all of you, all the finalists. It was very inspiring to see all your great works here. Thanks. And also thanks for all the people who've been with me during my master's and now during my PhD. Thanks.
Brilliant. Thank you. And that means we now come to the winner in the PhD category. And Dr. Klüver, would you do us the honor?
Of course. So this is the best, but of course also the toughest part, because as we've already heard, you've all delivered very good work, and it wasn't an easy decision. But we have to select someone, and I'm very proud to now announce the winner of the PhD thesis, and the Quantum Future Award 2024 goes to Dr. Sascha Heusen. Congratulations.
Congratulations.
Thank you.
And you get a cube too, of course. Yeah, better safe than sorry. Better safe than sorry. So, Dr. Heusen, you too, of course, are invited to say a few words.
Yeah, I first and foremost want to thank my supervisor, Markus Müller, and the entire group in Aachen. Also, thanks to all my friends and family who have supported me throughout, and everyone here making this fun event. I feel very honored. Thank you so much.
Now then, let's see how this works best. Perhaps we can sort of, from Julia Dräger, if you step a little bit over to that side, all of you, and clear that screen, because hopefully we will be able to see the graphic that reveals the winner of the popular vote. I've been watching it. There was quite a lot of people voting, and here we have the results. And it appears that Julia Dräger, you walk away with 2 prizes. You are also the recipient of the popular vote, but very close. Jana Fölisch, almost there, and Dr. Patrick Huber also made it amongst the top 3. There he is. Yeah, I know. But yeah, so congratulations. I don't have another cube for you or another certificate, but there is another prize going with it, of course. So now that we can see it, we can all come a little bit closer together again for our final picture. The jury members, don't be scared. Nobody's going to bite you. You can also come a little bit more into the center of the stage. So we have one final farewell. And Dr. Klüver, would you like to say some final words before I say farewell to our live stream audience?
Yeah, thanks a lot. So first of all, I feel like we are missing a round of applause here for the audience voting, so I would like to give that a chance. Congratulations to everyone who has won a prize from the audience as well. And yeah, what shall I say? It was incredible. So many very bright ideas, and the combination, I would say, of scientific excellence together with the good and great presentation skills and interesting talks and pitches. I think that was a very special day today, and I can only say thanks to the jury again for all your wisdom and your insights, and thanks for all finalists, and congratulations again to the winners. Thanks a lot.
Thank you. And with that, time flies when you're having fun. This wraps up the 2024 Quantum Future Awards. Thank you so much, everyone in the live stream who joined us, who also voted, and thank you obviously to all our finalists who were here in order to present their pitches, and also a big thank you to our guests. Big congratulations to everyone, and in particular, obviously, to our winners and the runners-up. A big thank you to the ministry who initiated the Quantum Future Awards, the jury members for their hard work, and well, I wish you a wonderful remainder of this year, and do already pencil down, there will be another Quantum Future Awards in 2025. Keep an eye on the website of the Federal Ministry of Education and Research, and quite possibly we'll meet again in November 2025. Until then, have a good time and keep up the good work. Congratulations again to everyone. And this is the moment where we will take some pictures, but you're free to go. Or ideally, we would like to have all the finalists on stage. I'm sure our photographer, we have a photographer here? You wear the photographer's hat, you tell us where to go.